Hello and welcome to Team FaultLine's Fall Symposium Capstone Project video for the SmartPDU1 Fault Detection Unit Integration. Let's begin. Our technical directors this semester were Brendan Smearbeck, software engineer, URI graduate of class of 2017, Mike Majdalani, electrical design engineer, URI grad class of 2018, Bill Owens, vice president of engineering at Acumentrics, Najib Ishak, consulting technical director for machine learning. Meet the team. Dylan Keyser, computer engineer, Anna Skelly, electrical engineer, Mackenzie Sherlock, electrical engineer, and myself, Oscar Ramirez, computer engineer. Acumentrics is a company headquartered in Wappel, Massachusetts, which was established in 1994. It's a trusted market leader in rugged uninterruptible power supplies, provides clean power, conditioning, and battery backups, and one of the preferred U.S. suppliers for power electronics in many of the world's largest defense contractors. Project motivation. The main motivation for this project is predictive maintenance. As it is becoming a growing interest across all industries, the main goal of predictive maintenance is to reduce all sorts of failures from devices and equipment. To do this, you compare the equipment's variance from something that is faulty from something that is in normal working order. So to give you an example of this is imagine an EMT unit out in the field and they get a distress call to rescue a survivor. Once they get to that survivor and they start using their medical equipment, the medical equipment fails. What Acumentrics is trying to accomplish is to predict when the equipment is going to fail. By predicting when it's going to fail, that EMT unit can send back the equipment and get it repaired before the failure so it can prevent the entire scenario altogether. Due to last year's team success on predictive maintenance on the Lasco fans with their FDU, we were tasked to integrate the SmartPDU with the FDU to create an all-in-one new SmartPDU FDU. Anticipated best outcome. We have two anticipated best outcomes for this team. Part of the first anticipated best outcome is to integrate the FaultLine FDU with Acumentrics SmartPDU1. Also to train the machine learning model using the SmartPDU1. Part of the anticipated best outcome 2 is to configure and test the FDU using three-phase power. Also to make sure that the machine learning model can train with three-phase power too. Summary of the team key technical accomplishment towards anticipated best outcome. We have gained an understanding of coding on the Raspberry Pi, gained knowledge of AC power triangle, NILM, and three-phase power, determined the FDU is configured for single-phase power, learned how to collect and pre-parse data using last year's team's FDU, learned how to train with the model, and also configured a new FDU board for single phase, which is currently untested. Economic impact for the company. This project will attract new customers while also pleasing current ones. It will increase the longevity of devices. It will grow market for predictive maintenance across all industries if it gets working. And this project will also allow Acumentrics to better understand all of their products' points of failures. Here's our block diagram for ABO1 and ABO2. I'm going to talk about the first two blocks in ABO1, mostly in reproducing last year's progress and removing THD, as indicated like this. And let's get started. So for my individual technical contributions for the semester, I finished the Google Crash Course on machine learning, which was not hard and not easy at the same time, as I was first exposed to machine learning this semester. Gain an understanding on coding on the Raspberry Pi, which was necessary because we're using a Raspberry Pi in last year's team's FDU. Learn how to collect data using last year's team's FDU. Learn how to train with the model, machine learning model. Compiled from source for TensorFlow for training, and we set up our training environment for training. What the last two basically means is we had an environment for running the model, but it was very inefficient. So we had to set up a proper efficient model, which reduced our time for training the model from 8 hours to a mere 1 to 2 minutes. So my key technical accomplishments which I wish to accomplish before April 16th of next year's is the completion of the first ML model without the THD features, then reconfiguring the FDU from SPI to I2C communication, reworking the machine learning model code to communicate with I2C and no longer SPI, and then finally the integration of the FDU into the SmartPDU1. And with that, now we'll pass it on to my fellow Capstone Design teammate, Dylan Keyser.
Thank you, Oscar. I would like to start off by talking about what exactly we plan to integrate into the PDU come spring semester. At this point in time, we have a model that is capable of reading power signature data from an appliance and performing inference using previously collected data to determine the structural integrity and reliability of our appliance. In order to reach this point, Team FaultLine first needed to collect enough data to mitigate chances of overfitting, which can occur when the data sets used in training bear too close of a resemblance to the point where the model is unable to make accurate predictions when given new data. The process of collecting data starts by plugging in our LASCO fan to the FDU. The ADE 7880 IC then reads the incoming power signature and converts the analog signal into a digital signal to be read by our model. Before this reading process can begin, our collected data must first be manually separated into 3 sets for training, validation, and testing. We then take our 3 data sets and run them through a pre-parse function, which serves the purpose of cleaning and normalizing these data sets. We can think of pre-parsing as sort of a translation function that will allow the model to read the incoming data. Once these data sets become legible, we can now begin training our model. The model trains itself using data from our training set before evaluating its progression using the validation set. We repeat this process of evaluating our models based off of the minor adjustments that stem from the validation results. Once this is complete, we will then use the trained version of the model that scored the highest validation accuracy to evaluate the model using the test set. When the model achieves a high enough accuracy using the test set, we are now ready to use this model to perform inference using the FDU. Similar to the collection stage, performing inference starts with the power signature data being collected by the integrated circuit. The IC then passes the digital signal into the inference script, where it is then cleaned and ran through the trained model in real time. The model's inference output is then cast to a set of LEDs, where green indicates the fan is working normally, as red indicates the fan is a faulty device. The additional blue and yellow LEDs are used to inform the user of what task the FDU is currently performing. Yellow is used for data collection, as blue is used for real-time inference. In order to effectively construct a model pipeline such as this, we need to be able to train our models at an efficient pace. The idea here is to have all of our training take place using the computer's graphics processor instead of the CPU. This is due to the GPU's ability to perform highly complex tensor computations at a faster and more efficient rate, in turn, decreasing the amount of time needed to train exponentially. Initially, when attempting to train, the model was unable to recognize the graphics processing unit due to a version inconsistency between Google's TensorFlow and NVIDIA's GPU drivers. The version inconsistency error can be solved by either attempting to freeze both programs at specified versions or by compiling TensorFlow from source. Ultimately, the team decided it would be best to compile TensorFlow from source, a solution initially determined to be a last resort due to the incredibly lengthy compilation time. The compilation process took 4 hours to complete using a 12-thread CPU, and I'm happy to report that the solution worked perfectly and the model can now be trained efficiently. The work for next semester begins by establishing a specific set of features and hyperparameters to improve upon, referred to as a baseline. This baseline feature set will then be further modified until we achieve the most optimal and efficient model we possibly can. Furthermore, I will be assisting my team in changing the communication protocol from SPI to I2C. The initial advantage for using SPI is the speed at which the protocol is able to carry and deliver information. I2C, while slower than SPI, finds its advantages when it comes to communication between a primary system and multiple secondary systems. This makes I2C crucial in achieving our anticipated best outcome. The final step is the integration of the FDU into the PDU. Once the PDU has the capability to perform real-time inference, The final goal is to configure the PDU to perform multiple inferences at once. After this step, the team's first anticipated best outcome has been achieved. I will now hand it off to Anna Skelly, where she will discuss the team's second anticipated best outcome.
Thank you, Dylan. Our team's anticipated best outcome number 2 is a continuation of last year's FaultLine team's project. Last year, the team was only able to complete single-phase fault detection on the FDU. The FDU board, however, is designed for single and three-phase power. So this year, along with working on integrating the FDU functionality into the SmartPDU, we are also making sure that the FDU works with three-phase power. This semester, we have determined that the hardware of the SmartPDU is capable of supporting the functionality of the FDU. This was a bit of a challenge at first because we needed to get up to speed on what the FDU and the PDU were capable of. This was essential to figure out before the CPEs on our teams could even begin to work on integrating the FDU into the PDU. The LEs on our team also gained an understanding of three-phase power. This is the majority of our anticipated best outcome number 2 as we continue working on the FDU. URI itself does not focus on power engineering in the undergraduate electrical engineering curriculum, so Mackenzie and myself needed to learn about this before we could begin to work on ABO2. To test the fans with the FDU, we have to take 2 fans, a good and a bad, a monitor, the FDU, a mouse, and a Raspberry Pi. This would be a really big struggle to carry all that yourself and set it up by yourself, so having an assistant is very necessary. In order to have a good working environment, we need the essential tools. Our Capstone lab did not have some of these essential tools in our solder stations. Since our team needed to use the solder station in order to populate the three-phase configuration, our team researched and purchased the necessary items needed for working on PCBs. Mackenzie and I had to do research on the FDU chips evaluation board and figure out what the correct configuration for three-phase power was. Once we had all of our necessary items in our solder station, we were able to populate the FDU with the three-phase power configuration. For our anticipated best outcome number 1, Mackenzie and I have finished the hardware side of this project, so we will be helping the CPEs in whatever endeavors they have for us. For our ABO2, the CPEs will then test the functionality of the FDU in three-phase power with low voltage. This is the best way for us to do it as students because 1, it's safe, 2, we don't have to find three-phase power source, and 3, we don't really need a load. We can simulate that in testing. Once we have done that and verified that it's safe, it's tested, it works, then we will test it fully with full power in three-phase. Now I would like to introduce you to the other ELE on our team, Mackenzie Sherlock.
Now that Anna has discussed the previous team's progress, how we caught up to where they left off with the FDU, and the modifications we made to the FDU to move from single-phase to three-phase power, I will now focus on the steps we have taken and will take to test our three-phase power configuration. As mentioned before, as ELEs, Anna and I compared the ADE7880 and ADE7816 chips for any differences in possible features and found a discrepancy with THD. We also worked together to populate the FDU for three-phase power, and in addition, I helped collect data for the ML model from a campus building using the original FDU. And most recently, we developed and began testing a method that will check if boards are working before we test to Acumentrics. While in the process of modifying the first FDU board for three-phase power, the question of how to test it arose. It became quickly apparent that URI did not have sufficient three-phase power to test the new FDU board with, leaving Acumentrics as the only testing option. Since the testing trip to Acumentrics, while possible, is time-consuming, especially when not prepared, the team would ideally like to verify that the items to test work properly, or at least as much as possible within the limitations of not getting to test it with three-phase power first. So, a preliminary testing plan for checking boards before this time-costly trip to Acumentrics was created. Here, we have a figure displaying the setup for board checking. Firstly, a function generator could be used to simulate AC power. While the chip is meant to analyze 3 out-of-phase AC signals simultaneously, the board can be verified as functional by checking the registers for each phase's inputs one by one. However, as the function generator will only generate low-power signals, inputting the signals into the test points that come after the voltage and current step-down circuitry can mimic the output of one of the phases of a more powerful three-phase signal after having been stepped down. Looking forward, the team will populate a second FDU, then, once the team proves that this verification method works on the eval board, the new 3-phase FDU boards will first be tested whether each phase appears to be working. After that, testing the boards with a typical 3-phase power source will be done at Acumentrics. Lastly, the ELEs will help the CPEs whenever possible, like assisting in tasks for PDU and FDU integration. As it stands, Team FaultLine is confident that the anticipated best outcome will be reached by the end of spring semester. The ML model has been reworked to more easily facilitate the removal and addition of features, meaning we have high confidence THD will be easier to remove. As reconfiguring the FDU for I2C instead of SPI requires only changing jumper configurations, the team believes there will be no issue changing communication protocols on the hardware side. Reworking the ML code from communicating with SPI to I2C may prove more challenging. The team has not had experience working with I2C before, so identifying and implementing the changes needed for the switch could prove more time-consuming than originally expected. While this risk exists, the team is still moderately confident this milestone will be achieved. The team has already populated one FDU board for 3-phase power, and is assured a second one will be populated similarly. The team has high confidence that the 3-phase FDU boards will be verified locally and successfully tested at Acumentrics, and that FDU functionality will be implemented within the SmartPDU by the end of the program. The team would like to thank the technical directors for their support. They have put forth the effort to be readily available, answering any questions we may have, as well as giving us valuable feedback on the progression of Project FaultLine. Brendan kept the team focused and on track, helping the team expedite the problem-solving process when issues arose, and was always available for questions on any topic. Mike assisted the ELEs in understanding the PDU and its makeup, and Najib was instrumental in understanding and touching up the previous machine learning model. The team could not have accomplished what they did without their help. The team would also like to thank Bill Owens and Dr. Sunak for providing us with the means and opportunity for making this project possible.